Hello, we're live. How's it going, everybody? So, who knows the big secret of Friday? Who knows what Friday is? It's Friday. No one knows. Friday's exam day. Yay, it's the first exam, right? It's in the syllabus. Should have put that stuff on your calendar. Should not come as a surprise to you. So, today I'm going to clean up the last couple things that I wanted to cover in preparation for the exam. And I also want to make sure that the CSVMs work so that in the event that some of you need them for the exam, or even all of you need them for the exam, they are available. So if you would please go to your CSVM and open that bad boy up and try to get into Eclipse. We are going to do a little stress test here or something just to make sure this piece of junk can endure all of us being on it at the same time, and that we can actually send traffic to each other. Because I realized that the things I was able to do last year on the CSVM are not necessarily the things I can do this year. So please take this opportunity during class to sign in, and then you're all going to send me some traffic using that sample. And I'm going to show you how to get stuff back and forth to the CSVM as well. It's going to be useful. So we'll call this network test. So I will come back to this in like 15 minutes because I know that's how long it takes to launch this thing and get into Eclipse. So for now, we'll talk about something else, but please go launch the CSVM. If you don't have it bookmarked already on Canvas, there's a discussions link, a discussions page, and I have links there, useful links, and one of them is the link to the CSVM. If you don't have it bookmarked already, you should. So yeah, sign into that. Sign into your CSVM, please, and we'll get back to it in like 15 minutes or so. Okay. Yeah, I'll leave this for now. Let's do the last few lab questions. This is one where a lot of people get confused. A shame we didn't get to go over this one. The old DHCP inform. DHCP inform. What does inform mean in classic English? What do you think is the meaning of DHCP inform? Why did they call it inform? Anyone have any guesses why it's called DHCP inform based on what you learned about it? It's an interesting word, right? You can try to give me the classic English definition, or you can just take a gander at why it's called inform. Does it mean that the client is informing the DHCP server of something? Is that why it's called inform? No, actually, it's not. It's kind of the exact opposite. It's DHCP inform stands for DHCP information. Pretty stupid, right? So they are looking for information from the server. So it's DHCP request for information. Now, unfortunately, information abbreviates to inform, which comes out to be definitely quite the misnomer. So the DHCP inform is sent out in a couple situations. So first of all, if you have a network where you don't use DHCP to configure IP addresses, you assign them manually. The DHCP inform goes out to gather some more information about the network besides IP addresses. Okay, second, even if you do configure your IP addresses with DHCP, like my network obviously did, your machine will occasionally send a DHCP inform to get information specific to the operating system. This is particularly true of like Windows computers, they will look for. I think what you saw in the trace was that it was looking for the domain name or the proxy group or something like that. So just some Windows specific info that it wants to have. And that's obviously going to be a new transaction after the IP is set up. And then the DHCP ACK contains that information. So whatever it is that they were asking for, whatever is available, the ACK won't contain all of the info necessarily. The DHCP server might not have all of the info, so it will just look, see what it's got, and return whatever it does have. So ICMP, Internet Control Message Protocol, or something. First, we were pinging 8.8.8.8. What is 8.8.8.8? Anybody know who owns that domain, what that is? Why do I pick that? Well, the why do I pick that is a really simple answer. It's because it's the easiest IP address to remember. I like to use 8.8.8. Also 4.4.4.4, 1.1.1.1. Those are all good, valid IP addresses that usually respond to pings. So if I need to see if my internet's working, I always go with 8.8.8 because I remember it. But what is it? It is Google's DNS service, their public DNS service. So you can use this for your own DNS needs. We'll talk a lot more about DNS in a week or so. But you can also use it to test your internet by pinging it. So this is a Google server. If you run a ping command on Windows, you should get 4 replies, 4 responses. So 4 requests, 4 pings, and 4 echoes. So 4 pings and 4 echoes back. If you try the IPv6 ping, it will probably fail because most people don't have Windows configured to do it. And that's basically as much of an answer as you need to give. It was just that something on your network doesn't support IPv6. Your operating system, your NIC, command prompt itself, a router on the way, something, but this fails for almost everybody. And it's a big IT headache to get IPv6 pings working. It's surprisingly obnoxious. Because I tried for this lab because I wanted to be able to do IPv6 pings. And even if you have a valid IPv6 address and everything, and you can communicate on it, for some reason it's just very hard to get IPv6 ping working. So if you trace route to 8.8.8, this plots a route to 8.8.8. That's trace route, trace route. And it does that with the TTL field. So to answer this question correctly, it says what's happening and what's the destination of all of these packets. So the destination question a lot of people got wrong. The destination of all of the packets is 8.8.8.8. The destination of the replies, the echo replies, that is your IP address. Okay, so you could have said that too. But the destination of all of the outgoing stuff, all of the requests, is 8.8.8.8. And what's happening to the TTL? Well, it goes up by 1 each time. That's what you needed to observe, that it goes up by 1. Each time your machine sends out a new echo request, it increments the TTL by 1. And how does this result in plotting a route to the destination? How does that change in 3, the increasing of the TTL by 1? So another hint that that's what I was looking for in your answer. How does that change actually give us all the destinations along the way? Okay, so let's sketch it out in Paint here for a second. Let's say that that's you. That's the next one. That's the next one. That's the next one. And that is your destination, right? So if you are going on a hop basis, so if you set the time to live to 1, your packet is headed for the destination. So during the normal course of things, right, it will go da-da-da, 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 da-da-da. That's how it gets to its destination, right? But if the time to live is 1, then it only makes it to this hop, and then this guy responds back with TTL expired. And that TTL expired contains this guy's route information, or this guy's IP address and everything. Okay, and so now you know this guy's IP address. But during the normal course of things, when you're just sending a packet to the destination, you don't get any info about the IP address and info of the routers along the way. Okay, when you set the TTL to 2, it completes 1, then 2 hops before timing out, and then this guy replies with his address. Okay, so now you have his address. When you set the TTL to 3, it completes 1, 2, 3 hops, and then this guy replies with his IP address. Okay, when you set the TTL to 4, it does 1, 2, 3, 4 hops, and this time you don't get a TTL expired. What do you get instead? Instead of a TTL expired, what do you get when you reach the destination? This is also the next question, right? Actually, next question. How do we know when the trace route is finished? So it's what happens when you've reached this destination. What do you get when the trace route is finished? A lot of people said when command prompt says trace finished. Okay. Obviously not what I was looking for. Come on, guys. I'm not looking for command prompt to say trace finished. So just because I did grade the last lab pretty generously, I set the floor to this one to 70, so you couldn't have done worse than 70. But in the future labs, I'll probably open up the floor a little and make it easier to do worse. Somebody said the inform. That is a different algorithm. I'm talking about ICMP now. Inform is a DHCP thing. So what do you get? These are all echo requests or pings. What do you get? Every time it times out along the way, you get a TTL expired response that includes the IP address of where it expired. And what do you get when you've reached the destination? What does that guy respond with once they actually are the destination? So another question too, if you've reached the destination and the TTL is expired, what do you do? Generally speaking, I think in the vast majority of cases, maybe always, it's probably the standard, it will not send a TTL expired if it is the destination. Because it doesn't matter if the TTL expired, but you've reached the destination. You've still reached the destination. There's no need to send a TTL expired at that point. But somebody said replies with a ping. Yes, so they reply to your ping. So the ping is the request, and the reply we usually call an echo. So the last guy, once they actually get your message, they're going to reply with an echo reply. Okay, so once you get a regular reply from your destination, that's when you know that trace route is finished. Now on to the next question. How do star fields in command prompt appear in Wireshark? Interesting, because this was a question that was really easy to answer just a couple years ago, and I originally wrote it, and now I guess because of better compliance with ICMP, almost every server will respond to ping. So I didn't really take off credit if you couldn't get this one, because pretty much nobody could get stars to show up. But it used to be that many servers would just not respond to pings, and so you would get a trace route that looked a little bit like this. You would this guy would respond, right, and then maybe the next one just wouldn't, and so what would happen is your computer would attempt to ping them, and they just wouldn't send anything. Okay, and so you would get one of two things. You would either get a destination unreachable, a port unreachable. That means that they've blocked ICMP and they want you to know that. So in that case, it's basically the same as a TTL, but traceroute isn't configured to use it. So you would get something called a destination unreachable when attempting to send your TTL2 to this guy, for example. Remember, the destination is always at the end. So when I say send to, I mean that it reaches them, and then they're supposed to send a TTL expired, but they just don't, because they don't respond to any kind of ICMP requests. The alternative is that they just send nothing, which became very common too. So that's the two answers you could have given: the ICMP unreachable, or just nothing. You would have a ping request with no reply. And what happens when that happens in traceroute is traceroute will just try 3 times, so it'll send 3 requests, and if it doesn't get one, it'll just move on to the next guy, because it's possible for a server in the middle to be misconfigured that way. And so if you send a traceroute to an address that doesn't exist, like I recommended if you weren't able to get stars. It will just try one hop, and those will all be stars, so it'll think, oh, well, there's nothing there. Okay, let me try 2, and then it'll send 2, and then it'll send 3, and it'll just keep going. I think it'll try something like 5 hops or something before it decides that there's obviously no route there. Okay. The times we see reported back to us are the round trip time. So in the command prompt, what you see there is the round trip time, how long it took the ICMP packet to make its journey to the router, and then how long it took you to get the response back. And you can observe that in Wireshark by looking at the send time of the ping request and then the response time of the echo reply. So if you use your time column in Wireshark and read off those two values, what time exactly, what delta did you get the ping reply at, the echo reply at, and what time delta did you send the request at, you can subtract and you can figure out a more precise RTT down to the hundreds value. So you were just supposed to do subtraction there. If you just showed me the Wireshark screenshot, I gave you all the credit, and I just left you a remark that I did ask for the value. So if you really answer the question, you would have done the subtraction, but it's fine. I know you're all able to subtract. So as long as I saw the column there where the subtraction had to be done, it was fine. A lot of people subtracted, it looked like the very first request with the very last echo reply. That wasn't the intent. You were supposed to just do 1, so get a better approximation for 1. But that was a valid answer too, I guess. Just this was a little vague after all. Okay, so how is it possible, and this didn't happen for everybody, but it does happen occasionally. How is it possible that some links in the middle of the journey have a longer delay than links that are closer to the destination? Let's try it in our VMware, which you should have opened by now. Friendly reminder to get into VMware so we can test it out for the exam. That's on Friday. Let me make my font bigger. Nope, that's a cursor. Let's see if we get any that are longer in the middle. It'd be interesting if we got stars here too, because then I would definitely know that none of you did it on the VM. Hey, look at that, I get stars on the second hop. Shoot, should have just told you guys to do it on the VM. Well, since a lot of you didn't get to see those stars, let's pull up Wireshark here. It'll only take a matter of hours before Wireshark is done starting on this thing. And then we'll be able to see some stars in our trace. Let's go with that one. Let me start this guy over. Huh. That doesn't look good. Alright, we'll just let that sit. And what do we get for the stars? We've got some time to live exceeded. So we see at the end, at the last one, we have a request and then a reply from 8.8.8. You'll notice it does send 3 of those because it wants to give you 3 times at the end too. So we know it's over. Actually, technically speaking, we get 3 pings with replies to them. Okay, so technically it's when we get 3 of them. Let's look for some stars. So here we go. We see destination unreachable, port unreachable. That's because the local router probably that services the CSVMs does not allow ICMP requests, and so it just sends you one of these port unreachable messages. So rather than time to live exceeded, which we get for all of the valid entries, we get a port unreachable message. And then we should see some more here. These are just timing out, but they're getting nothing. So these are stars, but we're getting nothing back. So this ICMP, this router along the way, chooses to not respond to pings at all. They just respond with nothing. And then we get normal time to live exceededs again. Okay, but good job, John Carroll, for having very fast internet. Look at that. That's 20 millisecond ping, that's gaming quality right there, guys. So if it wasn't a pandemic, I'd say go set up your rigs on campus and go play on those. All right, any questions about the lab? Oh, I didn't actually answer the last question. Why do some links in the middle of the journey sometimes have a longer delay than the destination? That wasn't the case in the trace that I just ran there. It looked like all of the ones at the end were the longest. But sometimes you see the ones in the middle have a longer delay. And that is simply because many routers, especially when they are busy, will deprioritize servicing ICMP requests. So they will respond to time to live expired, but they will do that as a kind of bottom priority. And same thing for ping replies. They'll do it as kind of a bottom priority. So sometimes you will see that the delays in the middle are longer because those routers, those servers are busy, and so they just prioritize forwarding traffic over responding to ICMP, TTL expireds and stuff. That means that when you send a ping to the destination, it actually arrives at the destination faster than an ICMP expired in the middle would have, just because that router would forward your ping instantly, but it would wait a few milliseconds before responding with the time to live exceeded. So again, it's a matter of congestion primarily. Okay. Now it's time to, let's see. I'm going to give everybody else another opportunity. We'll go to the next segment, and then hopefully by then everyone will have the CSVM open and running. So I'm going to go to, we're also stress testing it by just leaving it running and empty. Open up Eclipse and Wireshark too. That'll take you a few minutes. We're going to finish off these slides here. So we were talking when we left off about whether or not UDP was a datagram. And I said, well, sort of, because it doesn't really add much over IP, remember? And we said we were going to keep calling it a segment or a UDP datagram. Or we can be like Java and call it a datagram socket and things like that. Well, technically then Java is calling it a datagram, right? And the datagram socket is the socket for datagrams. So Java calls it a datagram. We'll try to be consistent with that too. So now let's talk about TCP, which we didn't go over yet. So we've already done UDP, and UDP was pretty simple. TCP is a little bit more complicated, but luckily Java abstracts away almost all of this stuff. It's still useful to know it, because we are going to do a little bit with it down the road. So first of all, TCP is session-based or connection-oriented. Hosts will first make a handshake exchange to connect with one another, and then once they've made that exchange, they are considered to be in a session with each other. Unlike UDP, TCP is full duplex, so A talks to B, B can talk to A, and that happens essentially over the same session, which means essentially over the same socket. We'll see how that works in a bit. TCP has reliable guarantees, so the receiver acknowledges the receipt of each packet. This is a little bit like a certified mail system or something. So whenever a packet is delivered, the recipient has to respond with some kind of acknowledgement, so a signature or something to show that they have received the message that was sent to them. As you can tell, this creates quite a bit of overhead, right? It's quite a bit of delay, all kinds of wonderful things. So that acknowledgement, which we call an ACK, can be blank. It's just an acknowledgement and nothing else. Or the acknowledgement can also have a payload. Think about how you might stuff a payload into the acknowledgement, or how you might generate a blank one. So we have the TCP header to look at. We have source port and destination port, just like UDP had. Okay, and then we have checksum, just like UDP had. And what else are we missing from UDP? Source port, destination port, checksum. Was there something else in the UDP header? Source port, destination port, checksum. Should I go back? Let's go back. Source port, destination port, checksum. Source port, destination port, checksum. Missing length, right? Missing length. Yep, someone said in the chat, payload length, right? We're missing payload length. Let's see. Interesting. So TCP header, if you don't have options, so again, another opportunity to put options. Unfortunately, because again, the options are seldom used, a little bit more often for TCP than for IP. But TCP is 20 bytes without any options. The source and the destination port should be self-explanatory by this point. They work the same way that UDPs do. Now, in order to get this session working, you need to know what order that traffic comes into. So remember, another one of the things that TCP guarantees you is that packets will arrive in order. And it accomplishes this using the sequence number. So when the communication starts, when the session is established, we agree on basically a randomly generated sequence number to start with. We try not to start from 0 for some cybersecurity reasons that we'll probably cover later. But we pick a sequence number, let's say 6, and the first packet that comes in is 6, the next one is 7, the next one is 8, the next one is 9. By putting that label on every single segment, every single packet that goes, it's very easy for the recipient to reassemble them in order, right? So if it knows that if it gets one with sequence number 7, and then it gets a 6 afterwards, depending on that machine's TCP implementation, it will just reorder them automatically and pass 6, 7 up to the application that is using that data, or it will drop those packets and ask to get them again, which we'll see how that works quite a bit later. So let's say that the sender wants to send 10,000 bytes, and the maximum segment size, the MSS, so this generally refers to the maximum size of the payload, is 1,000. Let's say that the sequence numbers for the 10 segments in that case will be 0, 1,000, 2,000, and so forth. Okay, and this is where you kind of get the length field, right? So instead of having the length field, you can use the sequence number. So we're not actually telling you what order of packet this is. We're actually telling you the order of the bytes. So in my example with the 6, 7, 8, that would be sending 1 byte at a time. What you would see in better practice would be something more like this example where you start with 6, sure, but then if you sent a 1,000 byte message, then you would be on 1,006, and then you would be on 2,006, and so forth. Still very easy for the recipient to order these things. All right, so the acknowledgement number is the next byte that this host expects. So the next byte, again, not the next segment, not the next packet itself, but the next byte that you expect. So if you've already received, let's say, sequence number 1,000. So you've received 2 pieces of traffic from that previous example. You've received 0 and you've received 1,000. So the ACK is going to be 1 greater than the last sequence number that you've received. So you would ACK 1,001. All right, so again, going back to that example, you would send 10 segments. The first one is a sequence of 0. The next one is a sequence of 1,000. Each segment contains 1,000 bytes because that's the maximum segment size in this example. Okay, so the sequence number of the second segment you get is 1,000, and you acknowledge the next byte that you are awaiting. That means the recipient would send an acknowledgement of 1,001. Now remember, that's in the header of every TCP segment. So you have a sequence number and an acknowledgement number in every TCP header. That already gives away a little bit of how you send a payload along with a sequence, right? So this communication, this thing can go both ways. Imagine that the recipient also wants to send 10,000 bytes to the sender at the same time. Note that their sequence numbers and their acknowledgements, in this example where we're starting everything from 0, will be exactly the same. So the sender sends 1,000 bytes with seek 0, and then the recipient would reply with ACK 1. Wait. Yes. Before it got it, it would reply with ACK 1 and send a seek 0 with 1,000 bytes of its own. Then the sender would have 1,000 bytes. They would reply with ACK 1,001 and a sequence of 1,000 which is their next message in the series, and then the receiver would do the same. So you can have both. You can have a payload with your own sequence numbers that are intended for the recipient, while at the same time acknowledging the last thing that you've gotten back from the sender. So your payload messages are often also acknowledgments. However, smaller packets arrive faster, so most TCP implementations will not send 1000-byte acknowledgments. They will choose instead to send an empty acknowledgment, knowing that it will arrive much quicker because it's better for TCP if those ACKs arrive as fast as possible. We'll see more of that when we look at its implementation in the labs and such. The header length, again, like we had in previous examples of the length, remember we had the length specified in the number of bytes, remember, which is confusing, right? So 32 bits, 8 bytes, or 8 bytes. So we've had the number of bytes instead of the number of bits, or instead of the length in bytes. Okay, so we had for the IP header the number of bytes, and it's the same thing here. You have the number of 32-bit words, and this was required due to options. And again, why don't they just do the number of bytes? Because it's a small field, right? So there's just not enough room in header length for telling you how many bytes this is total. So if this got to like I don't know, if there were like options up to 100 bytes long, then there just wouldn't be room for it. So instead we say how many 32-bit words, and notice that a row we generally think of as 32 bits. So this you can also think of as how many rows does this header have. Similar way of thinking of it for the other header that uses the same approach. How many bytes does the payload have in that case? Okay, so reserved. There was a lot of stuff reserved. There's this whole chunk right there. Good job for them for planning ahead. On the other hand, we see kind of a trend with networking stuff. We see that they plan a little bit for the future. It's easy to get the whole world to adopt a standard, relatively easy. IEEE or one of the other major internet commissions creates a standard, the whole world adopts it, okay. And this was especially true early on in the internet, 70s and 80s. But it's very, very hard to get everyone to change that standard. That's why IPv6 adoption has been so slow. So once the standard is set, almost impossible to make changes to it. And reserved is one of those examples of it being impossible to make changes for it. Because while many people have probably proposed wonderful things to do with that field, no one has agreed on a standard thing to do with that field. So now let's talk about the flags. Now these are all 1 bit, so these are very small. They're just yes or no. That's why they're flags. So just like when you're programming like a Boolean flag, these are all 1 or 0, yes or no. So here are the flags. First there's ACK, so that tells you if this segment is an acknowledgement. So if it has an acknowledgement in it, then you set ACK to 1. There's a SYN, like a sync, which is this the first message in a handshake? So we'll see the handshake protocol in a sec. The SYN tells you that this is the first part of the handshake. FIN, this is the last segment for this session. So you send FIN to close a session. Urge, there's urgent data in the payload. Some TCP implementations use urge in different ways too, but urge was intended to be used to deliver urgent data in the payload. What some implementations will do instead is set urge to 1 to pass data to the application or something. We probably won't see any alternative implementations, and urge isn't really used much to indicate the data is urgent today. It's not a particularly commonly used flag compared to the others anyway. RST stands for reset. I wasn't expecting a packet from you now, so I got basically an unsolicited TCP message from you. Maybe we don't have a session, or I wasn't expecting our session to still be open. In that case, servers that are properly configured should respond with a reset. So if we haven't established a session, you should get a segment that contains the reset flag set. And then push. which is process this now, also used to tell the application, here, take this data. So we'll see some use of push in Wireshark after we write our TCP example in Eclipse. We've got window. So let's go back and look at it here. We've got our window, the last thing before the checksum. We also have an urgent pointer later. Remember that, as it'll go back to urge. By the way, these are not in order. You'll notice that they don't go in that order in the header. That's not going to matter because in Wireshark they all come up individually, but they're not in order. Okay, so window is used for congestion control, and this is another one of those features. Remember, the TCP guarantees a little bit of congestion control. That means that if the receiver is swamped, it sets the window lower. If the receiver is able to handle more data, then it sets the window higher. So the receiver basically looks at its own buffer, and when it's sending its acknowledgments, or when it's sending its data to the other end, it populates that window field based on what its buffer looks like at the moment. So if its buffer is completely empty, it sets the window very, very small. If its buffer is full, it sets the window high. And that allows the recipient to have some information about how much traffic the sender is able to receive. So this is the first time that we see the recipient actually getting information about the network state of the sender. So the sender's basically their NIC and operating situation, how much buffer do they have, or anything else that would make them unable to receive more traffic at that time. They just would lower their window. And then we see the checksum again, same as UDP, just more error checking. So again, we have 3 layers of error checking now here at the IP datagram and at the frame using the CRC. We have that urgent data, so that's going to, when you set that urgent flag, you can set it for only, well, you do set it for only part of the segment. So you can say only the first 50 bytes or whatever of this segment are urgent. So the urgent pointer was supposed to mark the, last byte of data in that segment that is urgent. Okay, and obviously this is kind of a silly mechanism, so almost never used anymore. Alright, so the three-way handshake, very simple. Works much like you would expect a handshake to work in real life. So the sender wants to establish a session. They send a segment with the SYN flag set. Okay, so that's just a single flag. You flip to a 1. You send a segment. No payload at this point. The receiver responds with SYN ACK. So I got your SYN. I acknowledge it. Again, no payload. And then the sender sends that final acknowledgement of the SYN acknowledgement. And then we're all set. Now we can communicate. Our session has been established. So it's as simple as that. Those first 2 segments are empty, but the third one, the acknowledgement, can carry a payload. Why can that one carry a payload and the other 2 can't? And the idea is on why the third one, the final ACK from the sender, is permitted to carry a payload. By the way, if the sender doesn't have a payload at that time, or if it's expecting something from the receiver rather than trying to send something to them, then of course it wouldn't have a payload. It would just send a blank acknowledgement, an empty segment. So, SYN, ACK, and then ACK. Why does the last one get a payload? Because the session is already established at that time. They've begun communicating. This is the first, basically, segment of the session. The SYN and the SYN ACK are what's required to basically establish that session. This is the last part of the three-way handshake, but at this point the session is already established. The receiver is ready to get their traffic. The sender is ready to get the receiver's traffic, and so forth. So at this point, the session's good to go. We can send a payload along with that ACK. All right. Hopefully everybody has got on their CSVM. Any questions, feel free to put them in the chat. Otherwise, let's try to figure out how to move traffic over to the CSVM here. So I'm going to open up my Eclipse on this end, and then I'm going to open up Eclipse in my CSVM. So there's Eclipse in my CSVM. Look at that, I gave some of homework 4 away for you there. Someone asked, will the exam format mirror the labs? Yes, relatively similar to the lab in terms of what you have to do, but probably no written part, probably just some practical stuff where I want to see that you've gotten what you're supposed to get. I'm going to make a new package here called TCP UDP sample. Alrighty, go back to my real Eclipse. Let's find it. That's going to be TCP UDP review. So these guys here are what we were working on last time. We haven't gotten a TCP yet. So I'm going to go to Show In and System Explorer, and I'm going to find my Java source folder, my Java files there. And then I'm going to go back to the VM, and I'm going to click this nearly invisible bar on the left here. So you're going to click this bar on the left here to get this stuff to pop out. So just right over there, there's a little bar. You click it to get your stuff to pop out, and then up at the top here, there's an option for Open File Transfer Panel. So way up at the top, after you've clicked the bar on the left, pops up this thing, and you have this Open File Transfer Panel. It's one of the options at the top. It's the second one. Okay, so Open File Transfer Panel. So I'm going to click that guy. It's going to say drag and drop files into this window. The uploaded files will be saved in the My Documents folder. So back to my actual file system, I have these .java files that I would like to get over there real quick. So I'm just going to drag those guys in here. And there they go. And now I can close this out and close this out. And remember, it says they get saved in My Documents. So let's go hunt them down. I go here. I go to Documents. There's some other crap that I had before. So that's unfortunate. Now I have to figure out what's named what. So I'm looking for the ones named driver UDP client, driver UDP server, UDP client, UDP server. So this, and this are the ones I'm looking for. And then I can just drag those into my workspace once I've got them here. And then I will delete them all from my documents to avoid confusion down the road. Somebody said, I don't have that button. Ask IT. I don't know. I can't help you with that. You should have this button to make this thing bigger. Open File Transfer Panel. If you're using the desktop version, not the browser version, then it's possible that the button is in a different place. Anybody on the desktop version able to confirm that that's where the button is at? Anybody? When you have a wrong package name like this and you don't want to go to each one and fix it, the easiest way, guys, is to go to rename or simply hit F2 and just rename the package to something, and it will change all of the names of the stuff that's in that package too. Change all the package names in there. Takes forever, but it will do it. Well, it doesn't take forever on a decent machine. Yeah, anyone else confirm that they do have that button? Can anyone confirm that this system worked okay? They were able to click this guy, go to file transfer. Because I certainly don't want you guys to have to like open your email or something on the VM to move files. That would be very inconvenient. On the desktop version, open File Explorer on your VM, and you can see your physical computer's hard drive mounted on the VM. Well, that doesn't seem like a problem at all, giving John Carroll access to my whole physical hard drive. Yeah, that works, if that's really how it works. So apparently, you go just to this PC here, and you should see your physical drive mounted as well there, if I understand it from the comments in the chat. So I guess try that out. I guess you also have your H drive, so you could probably use Google File Stream here. Okay, whoops, that was my browser back button. Didn't think that would do that, so guess I gotta relaunch. Oh, that was quick. That was good the second time. Yes, I know my CSVM will be deleted. I get it. Thanks a lot. Okay, so don't hit your back button when you're using the browser version. Alright, so what I would like to do, system uptime is 16 days. A reboot is recommended. Sure. Okay, sounds good. I don't think I remember leaving it up, but alright, lovely. So I would like you guys to try to send me a message. So I am going to start the server. So I am running the old server. I don't actually see my console in this view. There it is. Okay, so what I need you guys to do is open up the client, and you are going to change the wrong one. You're going to change the IP address to mine. So let me give you my CSVM's IP address. And you will do this for the exam as well, so make sure you've got it all figured out. Now, the way we're going to do the exam, because we're all remote, is that you guys are just going to send messages to my local IP address. Okay, so that's going to be this one up here, this IPv4 address, which you should know if you finished the last homework. Okay, so copy, and it just occurred to me that I can't actually paste that anywhere, so I'll just make this bigger and let you guys look at it. So please change the IP address in UDP client to this one. So from 127.0.0.1 to this one. You may leave the port the same, and I am going to see if I can capture some stuff. Let's see. UDP.port equals 6112. Let's see if I get some stuff from you guys. So just try to send me some stuff, and we'll see if I get any of it. I got Are We Live? Woo! So yes, just change that IP right in UDP client there, and I should be able to get traffic from you. I got Garari Sucks. That hurt my feelings. Now the exam is going to be twice as hard because my feelings are so hurt. And we're getting that traffic in Wireshark as well. So let's read it in Wireshark. We got Are We Live? Garari Sucks. Hello, Dr. G. So if you are unable to do this, let me know, because you will need to do this or something like it on Friday. So you will need to send. I'll be using my VM as the host, and unfortunately they just blocked all of the outbound ports on that VM. How do I know that this is all the same person sending testing 107 to me? I know it's the same person because it has the same source IP, and it has the same port. It's the same port. Hello. Why do VMware suck? Lol, postponed the test. I got your IP send monies. Sort of. You got the IP of the VM. These things, when you connect to a VM, you don't know which one you're going to connect to, so you might not have the same IP today that you have tomorrow. The your actual desktop and everything could be hosted on a different VM that day. So we'll cover TCP next week. TCP won't be on the exam. It'll be just UDP. I might do like an extra or something for TCP, but it'll be mostly UDP on there. This test will have to be extended back. For the exam, will we need to run our code on the CSVM, or can we run it on our local machine? So you will probably need to run it on the CSVM because they blocked inbound traffic on the VM, so the VM can't get traffic from the outside world. So you can develop it on your machine, and that's actually what I would encourage you to do. Do it on your own Eclipse, and then just scoot it over using that fancy, nearly invisible side button when you're ready. This whole process shouldn't take you longer than 5 minutes if you have the VM open. And even if they all crash, as long as they come back online before the end of the exam, you can test it. And if they don't come back online before the end of the exam, then I'll just ask you to test it with loopback and then submit your source code, and I'll grade that. So we have all the contingencies ready here. But if it doesn't come offline, then you should be able to use the CSVM to finish the exam completely. Someone asked what content will be on the exam besides UDP. You know, it could be anything we've covered. I will ask you to observe things on Wireshark, and hopefully you know what's where. If you want to review something, I would review the couple of labs we did. There's probably not going to be like physical layer stuff on there, so I wouldn't bother with that. The most important thing is that you understand how to work UDP in Java, so complete the homework well, and that should prepare you well for the exam too. How long will the test be? 50 minutes? Yep. It will be 50 minutes. And we are out of time for today. Again, remember, if you couldn't get this to work, let me know, and we'll see what the issue was for you. Okay. And hopefully I have the same IP address next time when I sign back in. That would make it much more convenient. Okay, guys, that's it for today. It's actually quite over for today, so I will see you guys on Friday for the exam.